Ever wondered how your computer manages to transmit data without overwhelming the receiving end? The secret lies in something called flow control. This is a set of techniques and mechanisms designed to manage the rate at which data is transmitted between two communicating devices. It's like a traffic cop for data, ensuring that everything moves smoothly without any hiccups. Flow control is crucial for maintaining a smooth and reliable communication process, especially in networks with varying bandwidth, buffer sizes, and data processing capabilities. It's responsible for buffer management, ensuring the data processing rate matches the data arrival rate, and it helps to avoid unnecessary retransmissions, maximizing network bandwidth usage. But perhaps most importantly, flow control reduces packet loss and retransmissions due to congestion or overloading, ensuring our data gets where it needs to go. As you can see, flow control plays a vital role in ensuring smooth and reliable data communication. Now, let's delve into the different types of flow control mechanisms used in computer networks. First off, we have open-loop flow control, sometimes referred to as static flow control. This is a rather straightforward method where the data transmission rate is limited by predefined parameters. Once these parameters are set, they remain constant, irrespective of the network conditions. For example, a sender might decide to always send 10 packets per second, no matter what. This method is simple and predictable, but it's not very flexible. If the network is congested or the receiver's buffer is full, open-loop flow control can't adjust to these changes, which could result in data loss or unnecessary retransmissions. On the other side of the spectrum, we have closed-loop flow control, a dynamic form of flow control that is far more adaptable. Here, the sender adjusts its transmission rate based on feedback from the receiver or changes in network conditions. Suppose the receiver's buffer is nearing capacity. The receiver can send a signal back to the sender to slow down. Or if the network is free of congestion, the sender can increase its transmission rate. This ability to dynamically respond to varying network conditions makes closed-loop flow control more efficient and reliable. However, it's not all sunshine and roses. Closed-loop flow control can be more complex to implement and requires more processing power and memory. It also relies on accurate and timely feedback from the receiver. So if there's a delay in this feedback, the sender might not adjust its transmission rate quickly enough to prevent buffer overflow or underutilization. So you see, both open-loop and closed-loop flow control have their unique advantages and disadvantages. Open-loop flow control is simple and easy to implement but lacks flexibility. On the other hand, closed-loop flow control is adaptable and efficient but can be more complex and resource-intensive. While both types have their uses, closed-loop flow control is more versatile, capable of adjusting to changing network conditions. There are several mechanisms in place to implement flow control. Today, we'll explore some of the most common ones. First, we have stop and wait. This is a simple and straightforward flow control mechanism. The sender transmits a single packet and then patiently waits for an acknowledgement from the receiver before it sends the next packet. This method ensures that the receiver is not overwhelmed with data. However, it can be quite inefficient for networks with high latency, as the sender spends a good deal of time just waiting. Next up is the sliding window mechanism. Unlike stop and wait, sliding window allows the sender to transmit multiple packets before receiving an acknowledgement. It uses a concept of a window, which defines the number of packets that can be sent without requiring an acknowledgement. Once an acknowledgement is received, the window slides to include additional packets. Many transport protocols like TCP employ this mechanism. Within the sliding window mechanism, there are two notable variants: go back N and selective repeat. In go back N, if a packet is lost or an error is detected, all subsequent packets are retransmitted. This ensures no data is lost, but it can be inefficient if only a single packet was problematic. On the other hand, selective repeat improves upon this by only retransmitting the packets that had errors or were lost. This makes it a more efficient approach compared to go back N, especially in networks where errors are infrequent. We also have rate-based flow control. This mechanism allows the sender to control the data transmission rate based on feedback from the receiver or according to network conditions. This method is particularly common in networks with dynamic bandwidth requirements or in multimedia streaming applications. Within rate-based flow control, there are two common techniques: token bucket and leaky bucket. The token bucket technique controls the data rate using tokens. The sender accumulates tokens over time and can send data only if it has enough tokens. This mechanism is effective in networks where the data transmission rate varies. The leaky bucket technique, on the other hand, controls data transmission by allowing data to leak at a controlled rate. This ensures that the outgoing data rate does not exceed a predefined threshold, preventing the network from being overwhelmed. Each of these mechanisms serves a unique purpose and is suited to different networking environments and demands. From simple stop and wait to the more advanced sliding window and rate-based flow controls, these mechanisms ensure smooth and reliable communication between devices in a network. As network engineers, it's important to understand these mechanisms and their applications to design and manage networks effectively. Flow control is integral to the Transmission Control Protocol, Internet Protocol, or TCP/IP, which is the basic communication language of the Internet. Now, let's delve into how flow control is implemented in TCP/IP networks. 3 key mechanisms are at play here: window size, ACK-based control, and congestion avoidance. Window size in TCP/IP is a perfect example of the sliding window flow control technique. It represents the amount of data that a sender can transmit before requiring an acknowledgement from the receiver. The sender and receiver negotiate the window size during the connection setup, and it can be adjusted dynamically during the data transfer based on network conditions and the receiver's processing capabilities. This dynamic adjustment helps optimize the use of network resources and ensures smooth data flow. Next, we have ACK-based control. In TCP/IP, every data packet that is sent must be acknowledged by the receiver. If the sender doesn't receive an acknowledgement within a certain time frame, it assumes that the packet was lost or corrupted during transmission and resends it. This mechanism ensures data reliability, but can also lead to unnecessary retransmissions if acknowledgements are delayed due to network latency. Lastly, TCP/IP employs congestion avoidance mechanisms to prevent network congestion and ensure efficient data transmission. When a network becomes congested, packet loss increases and data transmission becomes unreliable. TCP/IP uses algorithms like slow start, congestion avoidance, fast retransmit, and fast recovery to detect and respond to network congestion. These algorithms adjust the data transmission rate and window size based on network conditions to prevent congestion and maintain reliable communication. So we see that TCP/IP uses a mix of flow control techniques to manage data transmission. These techniques work together to prevent data loss, maximize network resource usage, and maintain reliable communication, even in networks with varying bandwidths and processing capabilities. Implementing flow control in TCP/IP networks is crucial for maintaining reliable and efficient data transmission. So, we've covered a lot of ground on flow control in computer networks. We've untangled the importance of flow control, a crucial cog in the machine of data communication. It's the safety net that prevents buffer overflow, ensures efficient use of resources, and fosters reliable communication. It's the invisible hand that balances the data processing rate with the data arrival rate, keeping the scales from tipping into unnecessary retransmissions and maximizing network bandwidth usage. We've delved into the 2 main types of flow control: open loop and closed loop. The former, a static form, sets predefined parameters to limit data transmission. The latter, a more dynamic form, adjusts the transmission rate based on feedback from the receiver or network conditions, allowing for nimble responses to congestion and preventing buffer overflow. We've also explored the common mechanisms of flow control, from the simplicity of stop and wait, which involves transmitting one packet at a time and waiting for acknowledgement, to the efficiency of the sliding window method, which allows multiple packets to be sent before requiring an acknowledgement. We've also touched on go back-in and selective repeat, 2 specific types of the sliding window method that handle packet loss and errors differently. And let's not forget rate-based flow control, with the token bucket and leaky bucket techniques, which control the data rate in a dynamic and predefined manner respectively. Finally, we've taken a journey through the implementation of flow control in TCP/IP networks. We've seen how window size, acknowledgement-based control, and congestion avoidance play pivotal roles in maintaining a smooth and reliable communication process. Understanding flow control is key to grasping how data communication works, and it's a fundamental aspect of network engineering. Thanks for tuning in, and remember, keep your data flowing smoothly.